Okay. What we want to do in this lecture is to have more modeling by introducing gear train. And what's the effect of the gear train on the transfer function of a DC motor? Okay. So by the end of the lecture, we should be able to get the transfer function between theta L, and let's say if there is a motor in here in this side, okay, and let's say I have VA as input. So I would like to obtain theta L to VA. Okay, this is what we are going to do. But before we start, why do I need gears? Why do I need gears?
To transfer the motion.
To transfer the movement. Okay, what else?
Increase the power maybe of mechanical.
The torque. The torque. Look, usually in the motors we have high speed, low torque, and in the load most of the time what you need high torque, low speed. So we will use the gears to adjust these things, to adjust the speed and to adjust the torque. Now, let's take the analogy of this device to electrical engineering. Which device in electrical engineering will do the same job, similar job?
Amplifier?
Not quite. What else?
What job, doctor, again?
If
What is the job again?
the question is, I am taking, the speed and the torque from one side and changing it into another speed, another torque in the other side. What other device? What's a similar device?
Transformer?
Exactly. Transformer. What does transformer do? What do we do?
It changes the voltage and the current from one side to another side so that it can be used in a suitable manner.
You are absolutely right. We are changing voltage and current from one side, either stepping it up or stepping it down. Okay? Again, why do we step voltage up?
Well, for example, distribution purpose, we need to step it up so we'll not lose.
Because of the load.
Because of
to avoid losses.
Exactly. So in electrical engineering, in the power system, in the transmission line, okay, if we are, having the load far away from the generation, okay, you try to step it up so that the current will be, if we step the voltage, because look, the power is the same, and the power is the multiplication of the voltage times the current. Okay, if I am, increasing the voltage, I will be reducing the current, and the current is responsible for the heat dissipation, the losses in the line. So if I want to transmit over long distances, usually I will step the voltage up. And when I reach the, where I want to use it, I have to step it down. So I will use the transformer. By the way, do you know what's SKICO?
No.
Exactly. The question is, I was talking in the, this lecture in the last class, and I was surprised. I mean, some of you don't know what is SKICO. SKICO, the Saudi electricity.
This is problematic.
Exactly. It is responsible about, generating and, distributing the electrical power. Of course, now, SKICO, it used to generate all the power, beside Aramco, of course. But now there are private, investor where they do they generate electrical energy, and they sell it to SKICO, where SKICO can, distribute it to the consumers. Also now in recent year, the kingdom having, big movements into renewable energy. This is Division 2030, divisions that we will be using about, 50% of what we are producing from, renewable energy. It's renewable energy.
Yes.
What's renewable energy?
Like solar energy.
Solar or wind. Okay. In recent year, there was, there is great jump in, in the solar cell. Their prices went drastically. Okay. So that now, it's feasible to produce electrical energy from the sun or from the wind also. So anyway, this is because, I have sometimes certain point in discussion and all. I was surprised. Some of the students, they don't know what is SKICO. SKICO, as I said, SKICO is, one of the, when you graduate, hopefully you will work with Aramco, with SKICO, or definitely now these days, there is many, small companies in which you can work with. Let's go back to the gears. So, suppose, as I said, suppose I have a motor side in here, and this is a load. Okay? And I would like, when I connect the motor to the load, what will happen? I'll, put extra load on the motor. And as we said before, we derive the relationship for the motor between theta M and VA. And this was function of what? The relationship, a function of what, if you remember? The transfer function, if I'm not mistaken, is Km over S JMS plus B plus, time RA plus SLA. Do you remember this relation? Last time we derived this relation.
هذا armature control, دكتور ولا؟
Exactly, armature control DC motor. Suppose I have armature control DC motor. The same thing if you have the field control. Then the relation is going to be a little bit different. Now, suppose this is when the motor working by itself, there is no load on it. Now I'm connecting the load through the gear. So the load, it has its own JL and BL. It has the moment of inertia and the friction. The question is, how do I modify those two parameters in the motor side? Any idea, any suggestion?
How to what, دكتور?
How do
modify?
Look, this is, you have a motor working, it's rotating, and it depends on, okay, the moment of inertia of the motor and the damping of the motor. Now I am connecting it to a load. What do you think the load will, is there any effect of the load on the in the system?
Of course.
Of course. This effect will show by the modification of the moment of inertia. So I will be having what we call an equivalent moment of inertia and an equivalent damping factor.
How is that? How can you have equivalent moment of inertia for the system?
Okay. Well, suppose I have R1, L1, V1 or V input.
Ideal transformer.
Okay, what is the impedance from in this side? Reflecting.
We have to take the impedance from secondary and put it in the
And put
primary.
it in there through what? Multiplying it by what?
Allah, I forget صراحة.
By the turn ratio square, I think.
Yes, something like that. Yeah, there is a factor.
Exactly. Something like that. We would like to do that. We would like to do something. We'd like to modify, okay, J, okay, and B, and make it what we call an equivalent. I will say, let's me find J equivalent and B equivalent in the motor side. In here, I'm reflecting from the secondary to the primary. Okay, you take this what in circuit 205, EE205 or
213, 213.
213 and 360.
213. I don't know because they keep changing the name of the courses, and I didn't teach for quite some time, so I forget what I know. Circuit, I hope they did not change to 201. But 380, I think it's for quite some time they have it. So anyway, so basically the same thing which you have done in getting the equivalent impedance. If you have a transformer and reflecting it to the one side of the circuit, we would like to do the same in here. Okay, so we would like to find the relationship. If I would reflect JL and BL to the motor side, what do I have to do? Suppose this is what we have. I have a motor side and load side. In here, the motor by itself, it has a moment of inertia and damping factor. The load also, moment of inertia and damping factor. Okay. So the load is operating by itself, but now suppose I need to connect it to a gear, a load. Okay. Either you can connect, by the way, you can connect the motor to the load either with the gear or without gear. But suppose I'm doing it also through a gear, what will be the effect? Okay. Now, first of all, I assume the motor side I have, okay, in the transformer, you have number of turn in the coil, isn't it? In the gear, what do we have?
The radius.
turns ratio.
We have what we call them the teeth.
Yes, which is in parts that they are empty.
Okay, so N1 number of teeth in the motor side, and N2 number of teeth in the second side. Now, suppose this is S, this is R, the M, the radius of the gear in the motor side, and suppose this is theta. Call it
One teeth, Doctor. This is one teeth.
No, the look, the teeth, okay, or this side, it has, this is, what I mean? This is, suppose this is R1, look, this is R1, and this is R2. The radius of gear number 1, or the motor side. And R2 is the radius of gear number 2. And suppose I move it, I rotate, or let me rotate in this direction. So I will rotate in an angular position, theta m, suppose theta is very small. What will be the distance travel from here to here is s. What
R
will,
theta M.
what will be s
RM.
in terms of theta m and rm?
RM theta M.
What?
The multiplication of the two.
Exactly. So it will be rm theta m. This is the distance traveled by the first gear, or by the,
Radian يعني.
say that again.
Theta has to be a radian.
In radian, yes, yes. Now,
Doctor, can you repeat this one?
what I'm saying, you have rotational motion. And suppose the arc, I'm moving from this point to this point. And this is r, the radius, and this is theta. The motion in angular, and let me translate it into translational. If this is small, if the distance is small, I can approximate it by the radius times the angle. Well, usually it is r times sine theta, but we are, assuming theta is small, so the sine and the theta will be, they are the same. Now, if the gear are in touch and I'm moving the first one, what is the distance traveled by the second one?
The ratio of teeth.
No, wait. No, just tell me in terms of before the ratio. So if R1 traveled this distance, if this is, I mean,
It should be the same distance.
it will be the same distance.
Yes, but of course with the less theta.
With what?
يعني there will be compromises between theta and R يعني.
No, wait. It's going to be R2 or R load, theta load.
Right. Theta load will be less than theta M since R2 is greater
Well,
than
this,
R1.
okay. But,
Yeah.
I want to establish the relationship between the two.
Yeah, so the idea here is to equate the distance.
Exactly. But look, how accurate is this one? Is this perfect, or is this approximation?
We have damping, of course, and we have friction, and we have all of this stuff. So
No,
sometimes
no. I'm not talking about the friction. I'm talking about only distance. Think about the gear. Two gears are coming together. Okay? Is this exactly, we are doing approximation because look, in the gear, if gear 1 starts moving, do you think gear 2 immediately will start moving?
there will be a delay, right?
There will be a delay because of what we call the backlash. But in here, we are assuming they contact immediately, and this will be valid.
This is mechanical engineering. Before.
Well, yes,
Doctor,
this is from real life.
Yes, of course. Yeah.
Engineering. This is,
Doctor, the backlash is the small distance between the teeth.
exactly. Before they start engaging. But what we are assuming in here, they engage immediately. There is no backlash. But if you go, there is another course in control, nonlinear control system. They study the effect of nonlinearity. Okay? So, we are assuming, but what I'm trying to warn you that this is, there is an approximation here. Look, in real life, everything is nonlinear, but we are approximating. So, let me put the ratio between theta motor then to theta L will be what?
RL over
RL over RM.
L over R M. So this is one relation. Okay. Well, tell me. Okay. Okay. I would like to establish a relationship between. Okay. How many? Okay. How many teeth in R1 and how many teeth in R2?
We have N1 and N2.
So yes, but what is the, how do I relate them? R1 to R, sorry, let me call it M, and RL is proportional to N1 to N2, isn't it?
Yes, right.
The larger the gear, the more, the larger the radius, the more the teeth. But it is the ratio between them. So a proportionality.
How is it that? What's the relation?
What's the relation?
Yeah, maybe the radius is large, but why does that mean that there is more teeth?
What we are saying, okay, the number of teeth in the motor, okay, the number of teeth proportional to the radius, and the proportionality you can take it. So we will have, the number of teeth, okay, the radius of the motor, okay, to the radius of the load will be the ratio between the two.
Oh, I see.
Okay, why?
I thought you meant the radius of the teeth, not the radius of the motor.
No, it is, yeah, what I'm saying, this is the motor side. It's not the motor. It is the gear in here. The gear, it's not the motor. No, it has nothing to do with the motor.
Yeah, I mean the gear, sorry.
Okay. Now,
Doctor,
yes.
so far so good until now, but there is a comment I want to address. The theta or the angular position of gear 1 and gear 2 are opposite to each other.
Okay. What do you mean opposite? No. What do you mean?
Opposite. Theta M is minus theta L. لأنه
No.
بالعربي لو دورنا جير ماشي باتجاه الجير الثاني لازم يدور بالاتجاه المعاكس له.
لا بس look. Take the distance. Just take the distance. Traveled by the first one. It's equal to the same distance traveled by the second one.
We are not taking the displacement here.
I'm not taking direction. I'm taking pure distance.
Oh, okay. That's okay.
Okay, gear 1, let's say, move 1 centi. What's gear 2 will move also 1 centi.
Okay.
Okay, there is no directional. You are right.
Okay.
You are right. But I'm taking how much a pure distance. There's one more thing I need. What is the work done by gear 1? What is the work done by gear 1? And this is, remember, this is rotational motion.
It is the torque.
What?
The torque.
Yes.
Which is R multiplied by F, the force.
Not F, not quite F. Multiply, because the rotation multiplied by, no, it is basically the work in gear 1 is going to be Tm, okay, theta M. And the other side, it is TL theta L. We are assuming in here, there is no losses. The system is perfect. So if the system is perfect, then I am transmitting all the power from the motor side to the load side. Okay. So if this is the case, if we accept those 3 facts, then I will have Tm to TL, the last one, equal to, okay, R1 to R2, sorry, theta L to theta M, R1 to R2, N1 to N2. This is from the fact which we mentioned now. Okay, now suppose, as I said, the objective in here is to reflect everything to the motor side. So let me take T motor equal what in terms of the TL? T motor equal to N1 N2 TL. Do you agree? Use this relation.
Yes.
Okay. Now, what is TL? Apply Newton's law. What's TL equal to? Remember, Newton's law stated that the summation of the torque must be equal to the moment of inertia times the angular acceleration. Okay, so remember this equation. This is equal to, of course, N1 to N2 outside. This is equal to JL, the second theta L, dt square, plus BL, the theta L dt. Do you agree? Do you remember this relation?
Yes.
Okay. Now, this is Tm, and this is theta L. Let me change theta L in terms of theta M. Use this one. Theta L equal to N1, N2, okay, theta M.
Doctor,
Let's substitute.
Doctor,
Yes.
can you explain how you get the quantity inside the bracket?
The quantities, if you remember, suppose I have the rotational motion. This is the last time we, okay. Suppose this is it, I'm applying certain torque, okay. And I have this is B damping, and this is, let's say, shaft. Newton's law stated that the T, the applied torque, okay, minus what other torque I have in here? What other torque I have? I have the only friction torque, which is equal to what? The friction, we said, proportional to what? If this is moving, if this is rotating.
Speed.
Speed. So B times the speed, which is d theta dt. This must be equal to what? The moment of inertia times the angular acceleration. What's the angular acceleration?
Second derivative of theta.
The second theta dt square. So solve for t. T equal to what? J, the second theta dt square, plus b d theta dt. And this is basically what we have in here.
يعطيك العافية.
Okay, Allah yafik. Okay, now let me substitute for theta L in terms of theta M. So TL equal to N1, N2, okay, JL. Look, theta L, if you differentiate N1 or N2 is constant, so I can put it out, N1, N2, the second theta M.
This is TL, Doctor, or TM?
If?
This is TM or TL? TM, sir.
No, TM, yes, you are. Sorry. Thank you, Abdurrahman.
Welcome.
Plus B, L, N1, N2, d theta M, dt. Okay? let me put it in, this is the format. This is what I'm saying. Now, factor out the N1 over N2 out. So you'll have N1 over N2 square, JL, d second theta M dt, BL, d theta M dt. So if I want to reflect the load, okay, to the motor side through a gear, I have to multiply the moment of inertia by the turn square and the BL also by the turn square. Do you agree?
Just like the transformer.
Exactly. That's what I have said at the beginning of the lecture. What is the analogy in electrical engineering? So it is exactly the same concept. Okay. Well, so basically, if we want to talk about the equivalent, I said, what's the equivalent the motor will see if I have a load and the load is reflected through the gears? So the J equivalent equal the moment of inertia of the motor plus the load, the moment of inertia of the load, multiplied by, you know, the turn ratio square. If I don't have the load, then you consider this is 0 and this is 0, neglected, and then the moment of inertia of the motor remain. I mean, the equivalent motor, moment of inertia will be the moment of inertia of the motor itself. Okay? Any question here? So let's take an example. Suppose I want theta L to VA. Theta L to VA. By the way, what type of motor I'm using in here?
Armature controlled.
Armature control, because I'm keeping the field to be constant. Okay? So, if you remember now, look, in here we are using LA is almost negligible. It's 0. So first of all, let me write
شورت سيركت يعني
short circuit. It's negligible.
negligible.
Take the value of it equal to 0. So first of all, if you remember in last lecture, we obtained theta M to VA. And this is equal to, in the transform domain, this is equal to Km S, okay, RA plus SLA, but L equal to 0, so there is nothing in there, multiply by JS plus B, where now the J and the B should be modified according to what we have derived. So this is basically what I'm saying. Sorry, it is not, I did a mistake in here. It's not, it is, this is KMKB. No, but there is, wait a minute. I think, you know, there is definitely, I did certain error in here. So this is it. Okay, this is it. Km over S, RA, JS plus B, Km, KB. This is if you go back and see the derivation. Where in here I have to modify Jm in this way and B in this way. Now, how do I find, okay, how do I find my, you know, the question is find theta L to VA. So what do you do? So what do we do?
We can find, for example, theta L to theta M and then multiply it.
Exactly. If you remember, theta M, theta
L to theta, yes,
equal to, or theta L, sorry, equal to N1, N2, theta M.
That's correct.
I want to make sure that, okay, wait a minute. Yes. Theta L to theta M equal N1 to N2, or theta L equal N1 over N2 theta M.
Yes. They are directly proportional with the Taylor's ratio.
Exactly. So basically, this is the transfer function. Any question here?
Now this is motor with the gears.
With gear. And we have a load is connected to the motor through a gear.
And this is the electromechanical device, let's say.
Again, it's electromechanical. If you don't have any gear, take the gear ratio to be 1.
Right.
You just add the, the moment of inertia of the motor plus the moment of inertia of the load. I mean, if there is no gear, just take it directly.
So far, Doctor, in the course, we have just having some, let's say, important systems, and we analyze them.
Yes, we did not do the control yet. And we are not known. We are modeling now. We did not analyze.
Yeah, modeling, yes.
We are doing modeling. Okay, let's move. If there is no question, let's move into another topic. Very simple. DC generator. What does the generator do?
Converts the mechanical energy to electrical energy.
Exactly. Change the mechanical energy through the speed in here, okay, into an electrical energy. Okay. So basically the concept in here now, EG, this is the field circuit. So I'm rotating a mechanical, I'm rotating, certain conductors in a field. I will induce certain voltage. So EG proportional to what? EG will be proportional to K, okay, the field, and omega. Okay, in the generator, we take omega to be constant. Remember, before we have the back EMF, VB, equal to, again, K, phi, omega. Where we take in the motor side, the field is constant.
Because field is also proportional to the currents.
Yes.
Current.
So in here now, I'm converting the mechanical, which is omega, into the electrical. While in the motor, I'm converting the voltage into motion. Okay, now I would like to obtain, okay, the transfer function ET of S to EF of S. Let's start by the, okay, in here, of course, EG, we said proportional to the field, to the flux, to, okay, but the flux is proportional to what? How do I get
current?
The current, IF. So EG, you can think about it, EG equal to certain constant, okay, kg, let's call it, times IF. So if I want the transfer function, let me first of all, what's IF equal to? What's IF equal to in terms of EF?
We have 1 over R.
1 over R
RF plus SLF.
Sorry, EF. Okay. And we said EG equal to KG IF, which is equal to KG, okay, 1 over RF plus SLF EF. What's IA equal to?
EF. Why EF, دكتور? Yes, EF. Yeah.
So EIA equal to, or I can directly get ET in terms of EG
Exactly, yes.
by using voltage dividing rule. ET equal to, this is EG. What do I put in here?
RL
RL over
RL
plus
RA
the other impedance, which is R plus SLA. Now eliminate and you get the transfer function. So this is basically the transfer function.
Doctor, what is ET?
What did I do?
What is ET? What does it represent?
EG. What's EG?
ET.
Terminal voltage. E terminal. Okay, look. E terminal. ET, the terminal at the load. Now, let me ask you. Suppose, okay, now suppose, okay, suppose I have open loop system that I open this terminal. I disconnect in here. What's the relation between ET and EG?
It's the same.
They are the same because there will be no losses, no current. Okay, so this is if, you know, at no load, it means that I have open loop. So EG to EF is this relation. Okay, there is no effect for this side.
RL دكتور بإنفينيتي ولا؟
RL, how do you make open circuit? Yeah, you make it RL infinity. No, but you just disconnect. It's a system. You already have the system.
Yes, I can see because you know you just take RL.
Switch it off.
Yeah, you take RL and you put multimeter. So yes.
Doctor, KG here. KG represent the flux multiplied by K.
Yes. Look, this is what I'm saying. Let me go back. You want EG, okay? EG, we said EG equal KG times IF. Proportional. It's proportional to the flux and the speed, but we are saying the speed is constant. So it's proportional to the current, assuming that there is no, you know, I mean, no saturation. We are not reaching saturation.
But doctor, if we take RL out, if we just you know open the circuit, if we disconnect RL, so ET must be equal to EG.
Exactly, that's what we said.
Yes, yes. So this is the
whatever you are generating, it will be your terminal voltage because there is no losses, there is no current, there is no losses. Okay. Any other question? So this is basically if you want to put the block diagram, one at a time, you build it. Okay. If there is no question, we'll stop in here and have a nice weekend.
You have a wonderful weekend, Doctor.
الباور دكتور.
حياكم الله.